In this video, we're going to take a look at circular motion, which is accelerated motion, and it has certain special properties that we'll take a look at in a minute. But we're going to really clarify this and say that we're talking about uniform circular motion, which means moving in a circle at a constant speed. And then it's quite natural in the same vein to talk about gravity to address the circular motion of planets and satellites. So first of all, we have to recognize that circular motion is accelerated motion. There are three ways to accelerate: speeding up, slowing down, changing direction. And the relative direction of acceleration to velocity is going to be the indicator about which one of those three is happening. And of course, two can happen at the same time. You can speed up and change direction, or slow down and change direction. But if the acceleration has no component in the same direction as the velocity, then the speed is not going to change, but it will change direction. And that acceleration has a special term. It's called centripetal acceleration. And it has a special formula too. So this is one of those always things that you can jot down. Centripetal acceleration is always v squared over r. Well, if there's an acceleration, there's got to be a force. So the centripetal force, the inward pulling force, has always got to be there. And so that's what centripetal means. It means center seeking. Centrifugal is like center fleeing, but that's actually a fictitious force. It's sort of a reaction to being pulled inward. It's that you feel like you're going to be thrown outward. Right. So sometimes that's this force is provided by friction, like in our cars. And so the force of friction would be mv squared over r. But here are a couple of other situations where it's not the same. So I'm just going to skip out here. I'm going to take a look at a couple of amusement park rides. So this is the Gravitron, and it's like a spaceship. We see the operator is just going to sit in there, and it's going to spin people around them. There's the door just closed, and people are getting ready to go on this ride, and whoever's seeing the video is not really sure what to happen. So the operator is going to stay motionless, whereas this spaceship saucer ring is going to start to spin. And I was wrong about this because the operator is spinning along with the deck. It looks like it's bolted right in there. All right, so what the people are feeling is they're feeling an outward force as their bodies press against the outside wall, but it's the outside wall that's pushing inward on them that keeps them moving in a circle. So quality videoing there. And so they're pressed against the wall so hard that friction keeps them from falling. So maybe you've had a chance to go on that ride. Let's take a look at another one. And in this situation, in this amusement park ride, folks start off just hanging from swings. Sorry, a little extra background noise. And then the apparatus starts to turn. And if it's not enough, then the entire apparatus starts to lift out. So in this case, it's the tension from the chains that keeps them moving in a circle. Yeah, that's making me dizzy. So that's enough of that. And then lastly, sorry. And then lastly, let's take a look at Steve. Steve here is the stunt driver who's going to try and drive a car in a vertical circle. So let's see what that looks like. Yeah. Right. So the interesting thing is that the car doesn't fall down, even at its highest point. Right. Okay, great. So that's a little bit of background about centripetal force and some examples about things that can cause the centripetal force.